So let's continue. We were here from last time we were up to creating some classes, creating some properties in which there are two types of property, right? Remember that. Let me recap a little bit. There is, in terms of class, what we did is that you can create new classes, name them, right? You can define the classes that are in the same level to be disjoint. Okay, and of course, you can create a hierarchy having classes under the superclass and forming the structure of superclass, subclass, and so on. And this is what we call class hierarchy. You can then define properties in which there are object properties and data type properties. And both of them contain domains and ranges. Okay. So we could also define individuals or instances. In ontology, right, you can create an instance. So in this case, it could mean that you may have an instance of a pizza, an instance of some topping, cheese, bread, and so on. And the next step that I think we still need to continue and discuss in detail is about certain axioms in which you can define by our restrictions. And we will discuss three important types of restrictions, which is quantifier restrictions, hash value restrictions, and then cardinality restrictions. Okay. For these individuals, I think this is quite simple, right? If you have a class country, you can create an individual such as America, Italy, Thailand, India, Myanmar, and so on. Okay. So learn to distinguish again class versus instances or individuals. They are different. Okay. All right, then let's look at the axiom part. Before we go there in the detail, you need to make sure that your Protege works fine, right? I got some message from Paramik. You use 5.5, and actually version 5.5 is kind of pretty new, but did someone, has anyone used different versions? And okay, so everyone used 5.5 or what? 5.6.1. Okay, but what's wrong with Paramik when you try 5.6 or what? Five 5.6.1 doesn't show classes and subclass. I think they do. But which environment you use Paramik? Mac OS, Windows, Ubuntu, or which operating system? Windows.
Yeah.
Okay. Anyone use 5.6 on Windows? 10, right? And it's fine. Yes, I think it's fine, Paramik. But anyway, if 5.5 works for you, then just keep it. Even I started using Protege when it was version 3, then version 4, 5, but I don't remember which version I installed. Maybe I did not update to the newest one anyway, but it still works fine. So don't worry, we don't use the very new features anyway. But I think new features are kind of bug fixed and also maybe performance improvement and so on. But core features that allow doing reasoning, querying, defining classes, defining properties, defining axioms, they all work fine in even starting from version 4 and so on. Okay, so anyway, any version that works well on your machine, that's not a problem. Okay, so let's start. Let's continue with the the first type of axioms, which is called quantifier restriction. I think we learned this from the college level as well, undergrad level, in terms of logical condition using quantifier. I think this also based on set theory. Let me adjust this a little bit. Okay. Do you recall anything with this terminology? Existential quantifier or existential restriction, universal restrictions. These are related to, I think, that theory as well. Okay, anyone used to learn this? No? In mathematics, in logic class, have you learned this kind of symbol? Yes or no? Yes? How about no? No one seen this before? Let me know. No, don't worry. I will be teaching. So everyone has seen this, right? Okay. But your facial expression doesn't show me that you know this, but you didn't raise your hand too. So I'm confused as well. You call the symbol, but maybe don't remember the detail or what? Okay. Anyway, all right. For the let's look at it in an easy way from an example point of view. If we want to say that for existential, actually in the old day, we use the description saying that, oh, well, it doesn't. We say that, now even this doesn't work for me. Okay, let's try. Okay, we use the word sum, right? For sum and for all. That is what we learned when we were younger, okay? And what does it mean? It is used to express the relationship. For example, we want to say that a pizza must have at least one or actually some topping, right? To be a pizza. If you have only the bread, is it a pizza? No, you need a bread and you need at least some topping, right? Some means could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, fine, but cannot be 0, right? So that existential restriction here should mean that at least one, or for some, at least some, okay, having some. So this can be a class of things having at least one mozzarella topping. This is your mozzarella topping class. This could be instances of mozzarella topping, right? There could be many types of mozzarella topping instances. Then there's something, some object has this topping. Some object has this topping together with that topping. So something, not only pizza, right? But could be something else also has topping. When you eat ice cream, do you have topping? Yes, ice cream also has topping, right? Not only pizza that has topping. But anyway, we are focusing on only just the pizza. So we are saying we want to assert, or we want to say a condition that a pizza is a class containing objects such that object in this class must have the has topping property for at least one. Okay, that's it. So the way to say this is has topping some pizza topping. So this is a property. You are making restriction to a property. And this is the property has topping. Okay, you are making restriction to the pizza class, but on the has topping property. That pizza class must have topping, which is some pizza topping. This is the range. So actually, if you consider has topping property, the domain is pizza. Okay, the range is pizza topping. So we are restricting that pizza must have at least one property has topping connecting to the pizza topping. Okay, let's look at how about, no, it doesn't work. What if I change? Okay. Wrong. Okay. Anyway, let's look at the universal restriction. Okay, let's see this one, which means only or all. It means that suppose, okay, let's look at the example. Vegetarian pizza has only vegetable toppings, right? You don't allow, if you're vegetarian, you don't allow any meat to be there. So it means that vegetarian pizza can only have vegetable toppings. Or in other words, this means for all, right? So it means that for all toppings of vegetarian pizza, they all must be vegetable toppings. That's it, okay? So the way to assert this is to say, has topping property can only have vegetable topping, or a so-called vegetarian pizza. But if it is just any kind of pizza, it is fine, right? But if you are defining vegetarian pizza, you allow only vegetable toppings. Okay. Then, how do we do that? I hope you already did, right? Last time I asked you to practice and try. So the way to do this is by creating a new class, and then you can make an expression, okay, by making class expression and type in or use the user interface GUI to say that let's say this one, it is the pizza and pizza base restriction, right? But previous one, you can do the same using this class expression. You can create a vegetarian pizza or add details about pizza as well. Anyway, for this one, we are adding a restriction in this example, right? That a pizza must have a pizza base. Have a pizza base means have at least some pizza base. You cannot have a pizza without the base. Otherwise, I don't know how to eat, right? Okay. All right. So this one telling us that we can say has base. This is the property, okay, for the pizza class, such that it must be some pizza base. So when it is written, it will be like this, has base, some pizza base. So you will have two possible choice here, either some for the existential or only keyword for the universal. Take note that these are the syntax. So you cannot use your own word, right? It is the syntax for this class expression in ontology in Protege. Okay. Another example is to add some kind of pizza based on the name, right? As we already discussed, there are many types of pizza, such as many name pizza, such as margarita, you can create here some structure in a way that you first have pizza, then add a subclass named pizza. Then under name pizza, of course, you can add many more of the name pizza in your restaurant. One here is margarita. And we want to say that for margarita pizza, it has some mozzarella and it has some tomato toppings. These are our initial definition of margarita. Okay. So to do that, you can create, right? Making margarita pizza and then state the restrictions. Has topping some mozzarella topping, has topping some tomato topping, and is under name class. So everything here is a subclass of, and these are connecting through and. Okay, so it means the condition of margarita is that it is subclass of name pizza and has topping some tomato topping and has topping some mozzarella topping. So this is one way to define class definition. And this is, yeah, okay. Then what's next? Oops. Then suppose we want to add a few more types of pizza. Call it American pizza and American hot pizza. In a way that for American pizza, we define it to be having these three types of topping, right? Mozzarella, pepperoni sausage, and tomato. While for the American hot, is similar plus this one, right? The pepper topping jalapeno. And that's it. You could also practice and do the same. So that's all about the quantifier restrictions that you can make use of, existential or universal, for the keywords some and only. And with this way, actually, you are defining the restrictions on properties of your class, restricting some properties. Okay, the next one is not on how many properties you can have and the values of the properties, but the next one talks about the specific value. For some class, you may want to define that instances of this class can only have certain specific values. For example, we may want to say that mozzarella cheese, okay, in which we use it for mozzarella topping, is originally from Italy. So we can say that here, can I adjust this a little bit? Okay. We can, okay, let's say we have an object property, namely has country origin. And we want to define that our pizza, our topping, or all these things, right, can have this property, has country of origin. So you need to properly define what is supposed to be the domain. And then we could say anything. Oops. So I would say for some simplicity, the domain is just the thing, okay? And the range could be country, right? For this has country of origin. Anything could have country of origin linking to the range class, which is country. Okay, so if we want to say that mozzarella topping class can only have this value, the property has country of origin with which link to the value Italy. That's it. This is to enforce some restriction that for mozzarella topping, the value can only be Italy. Okay. Then the next type, right, is cardinality restrictions. We learn cardinality in several other courses as well, such as object orientation, class diagram, such as database modeling, ER diagram, and so on, right? We, when we want to say cardinality restriction, actually, we are defining exact number that individual of a class must have this number, this exact number of properties. For example, if we have a class student, usually we want to define, right, that a class student enroll, for example, program or degree. We may want to define that the cardinality is minimum 1, maximum 1. That means one student you can enroll for only one degree at some time, okay, for in one university at a particular time, something like that. Or you may have advisor, only one faculty, one advisor. So this also has cardinality 1 for the head advisor, right? Something like this. Okay. So you can define min and max cardinality for a particular property linking, defining a class, to define a class. So let's look at this example in the pizza domain. Suppose that we want to create something called interesting pizza. Our definition is that something interesting means it's rich of toppings. Okay, so in this definition in our restaurant, we want to say that interesting pizza has topping minimum 3. That's it. If your pizza has only 1 topping, it's not interesting. 2 toppings, no. 3, 4, 5, 6, 7, fine, to be interesting pizza. That's it. That is our definition of interesting pizza here. Okay. And this is the way, right? Some sample screenshots of how to define it. And when we define it in the class definition, it would become that interesting pizza is equivalent to pizza and has topping minimum 3. Okay, this is some kind of theory, formal semantics and some theory of logic related theory. There are 2 things. When we are defining something in the logical related theory definition, there are so-called what is called necessary conditions. Another one is if you want to go deep discussion, talk to Professor Du. Okay, about this stuff. Another is called necessary and sufficient conditions. Okay, what does it mean? Easy way to understand is to look at some example. Suppose that we have a class, name class in our ontology. You may define and imply that for this class, the necessary condition comprise these things. This condition 1, 2, 3, 4, 5, 6, 7, 5. These are the conditions define this class. Look at this arrow, it's just one way. Meaning that to be a pizza, for example, we should have topping, we should have this. We may have something else too. We define that what is so-called pizza class, and objects inside pizza class will have this condition. So once you have something which is pizza, this is pizza class. Once you have some pizza object, I cannot be too close. Pizza instance, okay, let's say, once you have some pizza instance, we can imply that our pizza instance will have this condition. Okay. Such as being I would say, let's say this is not actually a very good definition, but suppose, let's say, being a Thai citizen, Thai nation, I would have black hair, brown or black eyes, and this and that, right? So when you know someone is a Thai, you can imply without telling that how the person looks like, but you imagine, right, that, oh, that person who is a Thai should have black hair, black or brown eyes, and so on. These are necessary conditions. My example is not that good, right? It's not realistic as of now because there are so many Thai with the blonde and with this and that due to the mixture of the Asians and so on. But anyway, but how about necessary and sufficient conditions? If you look at this, you see that the arrow defines bidirectional. Meaning also that if something you don't know whether it's a pizza or not, you don't know whether it's an object of that thing or not, that class or not, but it has this condition. about it now? No. Okay. How can I fix now? Let's move it. I don't know what to do. Hello. Hello. Okay, better. Is it good now? The online student? I believe so, right? Use only one. How about it now? Okay. Is it good? Voice is low. Voice is low. Is it better now? Low or better? Still low? Yes means better. Okay. Okay. I hope it's good now. Perfect or not? Okay. I think so. At least the signal seems okay now. Where am I? Thank you for alerting. Okay. Okay. So let's. Were you at this point that you didn't hear me, Lakash and Paramit? I don't know where were you, but I hope it was when we talk about this necessary and sufficient condition. Okay. Let's try continuing this. And okay, I should not touch anything now. So with this necessary and sufficient condition, I was saying that if you have something, you don't know whether it belongs to that defined, we call it primitive class. Okay, that defined primitive. Okay. Okay, now it will not work. So with the primitive way of defining, it is just one direction here, such as in this example, we are defining cheesy pizza to mean that the condition of cheesy pizza is that it is a pizza with at least one cheese topping, right? Otherwise, it's not cheesy. So if I give you, hey, here, I serve you a cheesy pizza, you can imply, right? This direction, you can imply, I serve you cheesy pizza. You can imply that that cheesy pizza has at least one cheese topping for sure. Okay, this is just one way. But if I say that on the other way as well, if I have a pizza and also that pizza, one condition is that it is a pizza. Another condition is that it has cheese topping. Then I don't tell you that this is cheesy pizza. I tell you that, okay, here I give you a pizza with a cheese topping. Can you infer back that this is a cheesy pizza? If yes, this is the necessary and sufficient condition for something to be classified as cheesy pizza. Anything that satisfies these defined conditions can be implied to be in that category. For example, another example, I already said, right, that being Thai must have black hair and black eye. But suppose given someone with black hair and black eye, can you really say that this is a Thai? No, then it's not it doesn't work on both ways for that example. It's just implying this condition one way, but not the other way around. Okay, so that is why for being a Thai, necessary conditions mean black hair and black eyes, but that those necessary conditions are not sufficient to infer the other way around. That's the meaning. Okay. So there are quite a number of things when you define anything to work both sides. Okay. If you notice, I did not say, but I will say now. That is, if you notice here, with the equivalent class expression, you are defining so-called defined class. That means you are giving necessary and sufficient condition of some defined class. You are defining a class based on a definition. However, if you are defining a class using only subclass of here, you are making just one direction, such as this one, we are defining mozzarella topping, such that it is cheese topping and it has original, has country of origin from Italy. Is this defined class? Shall we make it equivalent definition, defined definition? If you do this, if actually I move this definition to be defined class, meaning that we are making necessary and sufficient condition. What does it mean? It means anything that is a cheese topping and that cheese topping which has country of origin from Italy will become mozzarella. Is it true? No, there are some other cheese topping from Italy which is not mozzarella, right? But maybe, I don't know. I'm not cheese expert, but I'm sure that is not the only thing, right? So they are not necessary and sufficient condition for you to infer them to be mozzarella topping. So it is like this. This is fine. This is already correct. Okay. And then let's move on. Any confusion? Let's practice more and more. I think this will be clearer and clearer. Think about being a Thai, being a Nepali, being something as I already mentioned, right? Having black hair, black eyes do not imply you to be a Thai, something like that. Okay, in my example. All right, the next part is to use a reasoner to make some inferencing of something that is not explicitly said, but it can infer more. Okay, for example, we already defined interesting pizza to be what? To be a pizza and having minimum 3 toppings, right? 3 pizza toppings. Then if you start a reasoner, without starting a reasoner, it's just defining the definition, right? But after starting a reasoner, then you can see that there will be, I will skip this first, there will be more of the infer classes based on the definition you define. For example, you should have seen the interesting pizza here. Okay. Before we only define definition, Later, it will, this is from the infer tab. Okay, this is asserted. Asserted means what you define. Infer means it includes also inference results in addition from the asserted. So after running the reasoner, the reasoning engine will yield this additional infer result. For example, we could get that these are cheesy pizza because it contains cheese topping. These are interesting pizza, and so on. Okay, back to what I skipped. But before, no questions, right? Back to what I skipped. When you want to start a reasoner, need to make sure you already download, plug in this and that as required from the beginning, right? There are quite a number of reasoners you can use. And actually, what are different among all these reasoners you could use depend on the reasoning service you want to use. But what we will use basically are basic. So any kind of reasoner available will do the work. Don't worry. There is Hermit, there is Palette, there is this and that. They work with all the things you are going to do. Okay. So in our example here, we use Hermit. But as I said, if even you choose and try other, they will work as well. Once you click start and then you choose already which reasoner to start, then it will run the reasoning and you can change between asserted and infer. One of the noticeable difference is that with asserted, these will have white background. With infer, it will become yellow. This is to easily visualize, spot the difference in terms of user interface. Mm-hmm. Yes. Yes. So that could mean that there's something wrong in terms of the way to assert the syntax or something is wrong. But I'm going to go a little further. And then if there are certain issues that doesn't work correctly, you can share the screen and we can discuss that what went wrong, what goes wrong. Okay. When you run your reasoner, and if you have this symbol, it clearly says that there's something wrong. That means there are some kind of inconsistency issue. That means you are conflicting the statements that you define. There are some conflicts in the statements that you define in your ontology. For example, what does it say here? Okay. For example, in this example, I'm not sure when you created your ontology, you may not have some inconsistency problem. That is good. But if there is inconsistency problem, the reasoner will not start and will not do anything. Because when there are conflicting statements, it means that something is still wrong. Then the reasoning result, inferencing result will go wrong and it will not yield. So in this example, is the example saying that there is some, okay, this is yellow. So this is in the infer mode. And when there is something red, it alerts you to check that something is wrong there. Okay. And here in this, we are saying that there is some, we intentionally, in this example, intentionally define a class, which is called probe inconsistent topping. That's very strange name, right? But it's just a name that we intentionally define it. Probe inconsistent topping. This one is defined to be a subclass of cheese topping and a subclass of vegetable topping. It is wrong and inconsistent because we used to define that these two class of cheese topping and vegetable topping, they must be disjoint. Then something that is a subclass of both is not possible. Such as you are having a class dog and a class cat, and you are saying that they are disjoint. You are defining one animal. Okay. And you say that this animal is a member, is not a subclass, okay? But the same thing. This animal is a member of dog class, an instance, and also an instance of cat class. Will that become possible? This is really another example of inconsistency definition. This instance cannot be an object of dog class and an object of cat class at the same time because they both are disjoint. Or if it is not an instance, but you're defining a class X can also not become a subclass of dog and a subclass of cat at the same time. And this is the same example of probe inconsistent topping. And it will alert you inconsistency problem in your model. Okay. So this is what we already discussed. With reasoner, you can use for checking how good your ontology is, at least it should be free of inconsistency. That's the first thing. So reasoner can help checking that at least you are not contradicting yourself in terms of modeling the ontology, in which it could happen when your ontology becomes complex and big. You might mistakenly define something. Second, you can use reasoner to infer, right? Or discover implicit knowledge or information, such as we discussed before, infer something like the interesting pizza and cheesy pizza. We never say that which pizza is interesting. We never say which pizza is cheesy. We only define the definition through the equivalent class, right? Define class. Then you will obtain this automatically from the reasoner. Okay. And the same can be done. And when you try and something doesn't come out, it could mean that you start and stop the reasoner one more time, or click at synchronize, because when you start the reasoner and you do some change in your ontology model, if you make change, you may need to synchronize the reasoner one more time to make it rerun, something like that. Okay. And what else in this example? Vegetarian pizza. This is also defined. This can be defined. You can define here. We use class expression to define a definition of defined class. Okay, so this is necessary and sufficient condition for the class vegetarian pizza, saying that it is a pizza, right, that has topping only cheese topping or vegetable topping. Only means something beyond this are not possible, right? Because otherwise, then we cannot eat that pizza if we are vegetarian. We allow cheese topping or vegetable topping only. And actually, cheese topping is a super class, right? You can have mozzarella, parmesan, and many types of cheese topping. You can have vegetable topping, which is mushroom, olive, and so on, right? You are not making definite fixed class, but you are making the super class constraint on the super class of the topping, but inside there could be very many things. And your real pizza could be made of pineapple. Okay, Italian people will get angry if you say pizza has pineapple. And you cannot have also tomato sauce. You can have tomato, but not ketchup or tomato sauce, something like that. Anyway, that's just some side story. Okay, so once you define this vegetarian pizza, you can run a reasoner, and it should include or infer pizza that can be classified as vegetarian pizza. So how can we use this? Of course, as I refer back, we are running a pizza restaurant. So our customer may come and ask, right? Oh, I am a vegetarian. Do you have vegetarian pizza menu? Originally, maybe you'd never classify anything as vegetarian, but you can define the definition and let the reasoner find out for you. And this way is similar to several of the papers, case studies you have presented or read or listened. That is like the COVID one. We define that to be confirmed case, to be suspicious, to be this and to be that. It means that we need to have this and that condition. You are defining something like similar to sufficient and necessary condition, right? And then you are inferring that who belong to which class or category. Okay, that's the thing. We will talk about open world assumption, which means that when you are saying that margarita pizza has mozzarella and tomato topping, when you say that margarita pizza has tomato topping, mozzarella topping, this is what you say. It doesn't mean, and you cannot assume that it has nothing else. It may have, but you don't say or you don't model. Okay, it is like I say, I am a supervisor or advisor of Duke, but it doesn't mean that no other students that I'm also supervising, right? I only say just some small, some partial, something. It may include some other things too. So the same thing is that we cannot infer that margarita is vegetarian because margarita may have something else in which is a meat topping. It only says that it has these two toppings, but it doesn't say that it doesn't have something else too, right? So if we want to have Margarita classified as vegetarian pizza. You must say that Margarita, instead of saying that Margarita has some, remember we have topping. For Margarita has topping, some mozzarella topping, has topping, some tomato topping. That is what we said, right? It means that it has some of this, but it doesn't say that it doesn't have the other things. So you must change from some to only. If you want to say that Margarita only have tomato and mozzarella, then we can safely guarantee that Margarita is vegetarian pizza, right? Okay, that's the thing. So you could do that by trying to say only mozzarella or tomato topping. Okay, and I think that's the main thing. The rest is some additional stuff allowing you to do Sparkle query, writing Sparkle to execute your ontology. Okay, and return some results. And also, actually, there are GL query. The example, the paper that Siri shows, I think it makes use of the DL query, the screenshot, that one. Okay, we may have a look later on in more detail. Okay, but as of today, I think this is all important stuff that we should have discussed. So we don't have enough time for sure for the proposal of your mini project. So we do it tomorrow after the reading. We start first by the reading, and then some of the proposal. We still have the afternoon session too. So bring what we learned from today. Okay. If there's still something you can improve, revise, or make some changes in terms of your mini project for the ontology design, please do, okay, for tomorrow. And then I can give feedback of what is to be improved or not, or it's already very interesting. But try to define what you're going to do and try to think of including inferencing mechanism, reasoning mechanism, right? Otherwise, just plain model. Okay. Anything from your side? If not, we see each other tomorrow, but we start from 10. For tomorrow, let's start from 10. I do have some other meeting, so I don't want to run and be late. So we start from 10 with the reading and then the presentation, and we continue in the afternoon a little more. Okay. Thank you for today.